Hello and welcome back. In this video we are going to test for conservative vector fields and in 3 space. Now remember we have a special name for it. We call this the curl. So suppose that m and n and p have continuous first partial derivatives. So remember this right here, if this is my vector space, this is the derivative of the function, the partial of the function with respect to x. This is the partial of our function with respect to y, and of course this is the partial of our function with respect to z. So these are my partials right here. This is considered conservative if and only if the curl of our function is 0. Remember, we call that irrotational, so our vector field is staying place. It's not rotating at all. That is, f is conservative if and only if, and we get the partial p with respect to y is equal to the partial of n with respect to z. And where we get all these rules, you might recall these all come from the determinant. Remember, this is my I component, my j component, my k component from the determinant. So you can remember from the determinant of our matrix. So you can memorize that, or you can just derive your determinant every time. So let's see here. We want to determine if the following vector fields are conservative. If conservative, we want to find a potential function. Now remember, where we get these is from our determinant. So let's kind of review that if we need to. We'll call this I, j, k. Remember, we're going to look at our gradient. The gradient of our vector is the partial with respect to x, the partial with respect to y, and the partial with respect to z. And on the bottom, we'll put our vector field itself. Our vector field, this was our m, n, and p right there. Now also remember, this is saying like our, if you think of this in terms of the second, these are also considered second derivatives. And we saw that in another video. Alright, so we can say this is going to equal, if I cover this, the partial of p with respect to y minus the partial of n with respect to z, I minus, cover that up, the partial of p with respect to x minus the partial of m with respect to z, j plus the partial of, now cover here up, n with respect to x minus the partial of m with respect to y in the k direction. And that's where these come. These have to be equal. Partial of p with respect to y, partial m with respect to z would be equal to each other. For the curl to be for this to curl to be 0, or for there to be conservative, these would have to be the difference would have to be 0, which means these would all have to be equal to each other. And that's what we're checking. So let's go ahead and find the curl. Curl f is what we call it. Equals. So if I look over here, here's m, n, and p. So we take here the partial of m of p with respect to y. This just becomes x squared minus the partial of n with respect to z, x squared. Good. That's going to be I minus the partial of p with respect to x. This becomes 2xy minus the partial of m with respect to z. This becomes x cubed y squared. Now I can actually stop here, because notice, this is equal to 0. This does not equal 0. So remember, for this to have a curl, for this to be conservative, everything would have to be 0. So therefore, our vector field is not considered conservative. Right there. And we're done with that one. All right, so let's take a look at example number 2 right here. So let's see here. We're just going to go ahead and use our rule. There's m, there's n, and there's p. So we're just going to go ahead and plug it in right here. So if I want to find out if the curl of our vector field, ready? It's going to be the partial p with respect to y, which is just going to be 1, minus, parenthesis, the partial of n with respect to z, which is just going to become 1, I, minus the partial of p with respect to x, there's no x, so that's just going to be 0, minus the partial of m with respect to z, there is no z there, so that's just 0, j, plus the partial of n with respect to x, that's just going to become 1 minus the partial of m with respect to y, which is 1k. And if you notice, this does equal 0, therefore this is considered conservative. Alright, so now what we have to do is find the potential function. And we kind of saw this last lesson where if we're in 2 space and in 3 space, it's the same idea. We're still going to start with one of our variables. It doesn't matter which one. So to get my potential function of x, y, and z, I'm going to start with y. So that's going to integrate y, but remember, this is the derivative of y of x. Right? This is, remember right here, this is the partial of my function with respect to x. So that is dx. And we integrate here, we're going to get x, y, plus our constant. But now, in 2 space, our constant would just be in terms of y. But now we actually have 2 variables. Our constant here is actually going to be in terms of y and z. Isn't that kind of crazy? Now, we have to pick. Well, which one do you want to solve for now? Y or z? I'm going to pick y. So to get y, I am going to take the antiderivative. So I take the derivative with respect to y. Right here. If I take the derivative of my function with respect to y, so the derivative of x, y plus c of y, z, remember this is going to equal to the y component of my vector field because they have to be the same. The derivative of my function, that's x, y, the derivative of my function has to be the same of my derivative of my vector field if this is conservative. So this is going to equal x plus z right there. And I can solve this. Well, the derivative here with respect to y, if I take the derivative with respect to y here, that's going to give us just x plus c prime of yz equals, well, the derivative here, this is just going to be x plus z still because that's not taking the derivative. Those cancel, and we get c prime of yz equal to z. And now I'm going to integrate, right? Now I'm going to integrate. Whoops, sorry here. Now I'm going to integrate. But remember, I'm integrating with respect to y, so c of yz becomes zy plus. Now, I'm going to get another constant, but now my constant's in terms of z. All right, so let's go ahead and write out what our current function is right here. F of x, yz equals xy plus zy plus my constant in terms of z. So now I'm just going to do this. Ready? Now I got to find z. Well, to get z, I am just going to take the derivative of my function with respect to z. So I'm just going to call it like this, a little bit shorter. F of z, the derivative with respect to z, well, that's just 0 plus y plus c prime of z. And what's that going to equal? The z component of my gradient, of my vector field. Remember, my derivative of my function has to equal my gradient field for it to be conservative. So this is just going to equal y right over here. And if you notice, the y's cancel, so you c prime of z equals to 0. And when you integrate, c of z just becomes a constant. So now my function f of x, y, z becomes xy plus zy plus whatever c of z is, which we said is just our constant, c, 1. And there's our function. All right, so that's number 2. Let's take a look at number 3. I promise number 3 won't take that long. Ready? I want to see if this is conservative, so I'm going to find the curl. To get that curl, ready? Remember, this is using my rule up here. I'm not going to reinvent the wheel. Remember, this is m, n, and p. The partial of p with respect to y, 0. Whoops. 0 minus the partial of n with respect to z, 0. So far, so good. Minus the partial of p with respect to x, 0. Minus the partial of m with respect to z. And here we go. E to the z, which does not equal 0. So, therefore, this is not conservative. Alright, so hope you enjoyed this video. Go into video number 2 and we'll take a look at a couple more examples about what does it mean about what's called divergence of a vector field. So we'll talk about that in the next video.